Hi, everyone. Thank you for attending this talk. My name is Mantas Naris. I'm a PhD student at the University of Colorado Boulder. And along with my collaborator, Jieqiu Shao, we have written a package for trajectory optimization in function space. So in the field of controls engineering, we are interested in dynamical systems. So these are things that have equations that govern them that generally take this form, like x dot equals f of xu. So some states that evolve in time and some external inputs that we can interact with the system. And specifically, we want to ask questions of optimization on these systems, such as how can a racing bike corner the fastest? Or how can a satellite, for example, adjust its trajectory or its orbit using the least amount of fuel? And questions of optimization like this are called optimal controls problems. And their solutions essentially affect every single walk of our lives. So it's very valuable to be able to answer them. Let's take a bit of a more formal look at this problem first, though. So the objective is to minimize a cost functional h, which operates on x and u, a pair of state and input spaces, which are continuous functions of time. And then f, l, and m are functions defining the dynamics and the stage cost and a terminal cost for the problem. Now, this optimal controls problem is generally hard to solve because it is constrained onto the trajectory manifold of the system, which is generally defined by nonlinear dynamics, or can often be defined by nonlinear dynamics. So this trajectory manifold is defined as the subspace of these state and input spaces, x and u. And any given trajectory, c, which is a pair of these two functions, can be said to belong to the trajectory manifold if it obeys the dynamics of the system and the initial condition. So we can rewrite this same problem with a slightly different notation, kind of grouping these x and u's into a trajectory like so. Now, the standard approach would be to discretize this problem and transcribe it as a nonlinear program, but doing so makes essentially a fundamental trade-off between the accuracy of the solution and the computational cost required to reach it, because we are approximating this trajectory manifold. When in reality, the manifold itself is precisely the search space for the solution to our optimal controls problem. So what if we didn't have to make this trade-off? What if we didn't have to do any sort of discretization at all and could instead solve this problem directly in the Banach space in which it lives, so an infinite dimensional function space? And PRONTO is the projection operator-based Newton's method for trajectory optimization. It is an algorithm created by Professor John Hauser in the early 2000s, and it solves this optimal controls problem directly in the infinite dimensional function space. So as such, it does not rely on any sort of discretization of the dynamics and is particularly well suited for solving large problems that need a particularly accurate solution and fairly complex dynamics, or in the face of fairly complex dynamics. However, this algorithm is fairly mathematically complex and is generally difficult to use without having the right skill set to operate it. So our goal was to implement a version of PRONTO that made this tool available to make this tool available to a broader research community. And so Julia was a particularly attractive choice for this. Given by the fact that I'm here, we use Julia for many reasons, including automatic code generation and all of the different tools that could make setting up this problem easier, but also for actually solving the problem. We have access to some of the best-in-class ODE solvers, and also the general code that you get when you write in Julia tends to be fairly transparent and provide some insights into potentially actual mathematics of what's going on in this algorithm for people to continue developing and contributing to it in the future. So an overview of how the PRONTO algorithm works. Step one, we design a projection operator that can take arbitrary state and input curves and map them onto the trajectory manifold that we are interested in. Then we calculate a local search direction, again, in this function space, which we do by essentially solving a reduced optimization problem on a tangent space to the current trajectory iterate. And then we determine, kind of dial in the step size by a backtracking line search, and then use the result of this, essentially the combination of the step size, the search direction, and the projection operator to take projection back onto the manifold and use that as our next iterate. So in a bit more detail, designing the projection operator. The objective of this is to be able to explore beyond this trajectory manifold for the sake of actually iterating through the problem. So this operator would need to map, or essentially be able to convert our constrained optimal controls problem into an unconstrained one. So going from something that is constrained to the trajectory manifold to something that is not. And this operator would have to be able to map things from the state and input space onto the trajectory manifold. So say you have a curve C that is a trajectory or a curve eta that is not. This projection operator would potentially look something like this. Basically, take the inputs of the input space and just plug them directly into the dynamics that you already have. This would essentially simulate the system with a different input, and you could guarantee that the result of this, the input and state pair that you would get, would in fact be a valid trajectory because you've attached all of the constraints that make it one. But this isn't particularly useful because it pretty much throws out all of the information of the state that is stored within eta. So we augment this with a regulator. Essentially just turn this into a closed loop control problem. And this then lets us also pretty accurately track the state that we're interested in, but essentially convert this arbitrary curve into a valid trajectory. So to do this, common approach is to use LQR. We can just essentially solve the Riccati equation backwards in time from a terminal condition, which is usually defined by an algebraic Riccati equation. And we do this with using Jacobians. The fx and fu that you see in there are the Jacobians of the dynamics evaluated around the curve eta. So yeah, this is a pretty useful approach. And then by solving this, we have now an operator that we can use. So the next step after this is to determine the search direction. This is done by solving a reduced order optimization problem in a tangent space to the current trajectory. And so the first step of doing so is to just take a look at the tangent space itself. So this is also defined with a linearization of the dynamics. And now with this, we want to find a search direction that will take the cost of the next step. So if we take our current trajectory and our search direction and add them together, that should be addition, it should be lower than the cost of our current step. So to find this, we can take a second order approximation of this difference. And this is done by Taylor series expansion, but using Fréchet derivatives, because we're doing everything with functionals. And then the search direction will be the minimizer to solving this, this problem. Now, if we take this form, we can step through all of the different chain rules and derivatives and essentially expand this thing out to look something like this. And this is a linear quadratic optimal controls problem, which is something that in the field of controls we know how to solve analytically. First, solve a series of Riccati equations backwards in time from some terminal conditions, which gives an optimizer of sorts. And then we can use this information and solve back forwards in time to propagate that along the tangent space. And that gives the search direction. Essentially, with a reduced order representation of the system, locally sort of speaking, in which space do we have to step down this infinite dimensional manifold in order to reduce our cost? So, however, since we're solving a reduced order problem, we don't necessarily know if the step size that we took quite lines up with the actual manifold itself. So we want to be able to essentially dial it in a little bit and step back along that search direction to see whether or not we can essentially find a cost on the actual trajectory manifold that has a reduced cost from our previous step. So we do so by augmenting everything with this value of gamma, and then doing a backtracking line search essentially along this search direction using costs evaluated after applying the projection operator until we satisfy an Armijo condition and essentially get our step size. So once we have that step size and the search direction and a projection operator valid for our current trajectory iterate, we can combine those to then take the next step. Basically travel in the search direction, the correct distance, and then project back onto the manifold to get the next trajectory iterate. So the actual algorithm itself gets fairly mathematically involved. There's several papers I'd be happy to point to if you want to know the details. So, but a quick summary, design a projection operator, find a search direction, adjust the step size, and then update the trajectory iterate. So with all of that said, the challenge of implementing this in really any language at all is being able to take a problem that's defined by a couple of functions or functionals that the user might be, or that someone solving the problem would be interested in actually thinking about, like things that define either the dynamics of and the behavior of our system, or things that we prescribe in order to design an optimal controller according to a certain set of rules that we're interested in. But taking those things and translating them into a series of differential equations that are vector or matrix valued that have to be solved alternatingly forwards and backwards in time over and over in a loop. And to solve them, you also have to take Jacobians and Hessians of these original functions that you're actually interested in and evaluate them along a trajectory, all in the process of solving these differential equations. So that in and of itself is complicated. But furthermore, so when we implemented this, we were able to just plug everything into differential equations.jl, and that was great. However, we were not able to just pass ODE solutions around in a loop because differential equations uses lazy evaluation to represent its solutions, which is a very efficient thing to do if you're only interested in solving a problem once and then using or taking a look at that solution. But chaining these things together slowly leads to an ever-growing, essentially, call evaluation chain that gets very, very expensive to compute with increasing steps. So we had to slightly modify the actual solution representation from differential equations in order to basically force some interpolations and break that chain occasionally. But fundamentally, the challenge of this is making this friendly, making this, wrapping this in some sort of interface that is accessible yet performant. And so to show you how we did that, let's consider sort of a toy problem in nonlinear controls, which is stabilizing an inverted pendulum. So let's say we want to take a pendulum and steer it to a state where it's perfectly balanced vertically. So the first thing that we would do using PRONTO.jl is define a new subtype of the model type. This directly in its type definition encodes the size of the model, so the size of the states and the size of the input space. And we can also plug in any sort of parameters that we're interested in using. So that gives us the ability to explore parameterizations of the model when we're done. However, the most important thing of defining a struct like this is that that also then lets Pronto internally dispatch using the type of the model to essentially achieve polymorphism on that massive equations I showed on the other slide. So once we do that, we can encode the dynamics, and here I use a pretty trivial stage and terminal cost. If you're doing this on a real problem and we're doing real controls engineering, you'd obviously spend a lot of time thinking about these things. Q and R are some regulator matrices for the LQR for the projection operator. So this is what defining the problem looks like in PRONTO.jl. And the next thing that happens is a code generation step. So it's important to note something like this is not a function, but it defines a symbolic expression that Pronto can manipulate. It uses the information from the type definition to essentially generate a palette of available symbols that we expect Pronto to have. So you can sort of conveniently use the parameters that you attach to your type. It just makes defining the problem a lot cleaner. But then this thing is traced symbolically, passed into symbolics.jl, differentiated, or potentially for some of the things we actually do some symbolic simplifications and symbolic algebra. And then we generate the customized versions or customized methods for our inverse pendulum that essentially plug into the dispatch or the method table for Pronto. So what that generated code looks like. So this is just for the actual dynamics function that Pronto would use. We basically spit out 3 different functions. One that does the memory essentially management for numeric types, one for symbolics, and one for that actually does the proper computation in place. And we follow this sort of similar pattern from just that one definition for all of the Jacobians and Hessians of this system. So you can imagine doing something like this, which is a requirement for using Pronto, gets very, very labor intensive for much larger systems or systems that have some less friendly dynamics. And so this in and of itself is a very valuable time-saving tool. Pronto ultimately needs about 20 functions to be defined, or functions to be generated, and those get populated when you do this. So the next step is to actually run the model. So you first instantiate an instance of the actual inverse pendulum type. Since we did it with the keyword arguments, you can also modify any of the parameters that you want in there. Define a time window, some initial conditions, and then generate a guess trajectory. So the smooth function is something that we defined that basically draws a smooth line between 2 endpoints and then applies the projection operator so that we can actually feed a valid trajectory into Pronto to start the algorithm. So let's say we use a particularly bad guess, essentially, for our trajectory. So just set the trajectory to the final value that we want, which isn't even a valid trajectory of the system. Running that through the projection operator would map it onto a valid trajectory, but one that is maybe not something that we'd actually want our pendulum to do unless you have a particularly torquey motor on your system. So passing this into Pronto, and lets us optimize it, which looks something like this. And there we go. I would like to take a quick moment to acknowledge probably the greatest package ever written, which is UnicodePlots.jl. Since we were representing our solutions in kind of a custom wrapper object, we were able to map just the Julia show method to generate a plot of our solution, which we found was 1,000 times more intuitive than just staring at the stream of numbers that it spit out. So yeah, let's talk about performance. So this here is a state-to-state transfer of a 2-level system. Up above is the Schrodinger equation that describes it, and the control objective for this would be to essentially steer this system from its 0 state to its 1 state. And there's a quick comparison of a couple of different algorithms here. So we compared 3 different implementations of Pronto. We have one that was originally written in C++ that used Simulink to solve the ODEs, one that was written in pure MATLAB, and then our PRONTO.jl. We compared it against Koratov.jl, which is basically a state-of-the-art algorithm used to solve quantum optimal controls problems. So here you see on the bottom is the number of iterations that each algorithm took, and the y-axis is the descent. So you can see Pronto, all three implementations of Pronto achieve quadratic convergence and can solve this problem in 4 iterations instead of, I believe, 18. However, also, it does it quite quickly. You would expect, we would have expected a quadratic step to essentially be more expensive to solve, but that might not necessarily be the case. So, and the fact that we were able to actually, we were originally hoping to write this in a way that was easier to use first and perform it second. We ended up getting both, which is awesome. But that said, if we take a look at a profile trace of this thing, we have plenty of optimization potential still left in this package. There are some things that I'm doing that I should do differently. And so, yeah, it's exciting to see where this could potentially go. Yeah, so some applications. Pronto in the past, over the past 20 years, has been applied to everything from motorcycle dynamics to underwater vehicles to satellite trajectory optimization. But now PRONTO.jl has recently been applied to quantum systems. So one example that I'd like to share, one project that I'd like to share is shaken lattice interferometry. So our collaborators over in the CU Physics department set up this experiment actually on hardware where, like, let's say we want to build an atom-based accelerometer. The way that this would have to be done is by taking a Bose-Einstein condensate, shining a couple of lasers on it, one to measure the system, one to actually cool prepare the Bose-Einstein condensate, and then one laser lattice that could potentially control it. And our objective would be to design a control, or was to design a control sequence that would let us actually do the shaken lattice interferometry. And here are the results. So at the top, you see the control sequence generated by PRONTO.jl. And at the bottom, you see the actual experimental results from the physics lab. Both evolve over time. So on that bottom one, you essentially can see like slices in time. And what it shows is, so the top is just a pulse sequence. The bottom is, shows the density of a cloud of atoms. So the first step of the sequence is to split this cloud from a single starting point to two separated clouds. Then the middle takes this, reflects the position of those two clouds against each other, and then the third portion of the sequence brings them back together. And what's particularly exciting is that a result like this has never been demonstrated experimentally. This is, as far as we know, the first time anyone's actually been able to achieve this result in the lab. And so we were able to achieve our objective, which was to make Pronto accessible to researchers doing real experimental work in the field. So we're very excited to see where else it might potentially go. And there's plenty of work still left to do. I talked about code optimization. Reduction in compile times is definitely something to think about because we're generating a lot of functions. So we can't leverage some of the tools that are available for that. We want to explore sparsity, addition of constraints, proper true variable time steps, and then potential integrations with any number of things in the Julia ecosystem. Finally, there's automatic differentiation to consider versus symbolics as kind of the driving engine for this thing. So I would like to take a moment to thank our team and our collaborators and open up the floor to any questions. In maybe I have one question.
Hey, thank you very much for the nice talk. And I love the uniplots used in the terminal and also the comparison that you've drawn from your method compared like to discretizing everything, which is quite appropriate. You know, I guess my question is about that. If you take the approach of discretizing everything and then just passing that to using an off-the-shelf nonlinear solver to formulate your optimal control problems, then if things like joint positions, velocities, and torques are your decision variables, it becomes very easy to define constraints on the state and the control. So you can just like say, I want to have a linear inequality, an upper bound and lower bound on my minimum and maximum torque that the system is able to produce. How does it work on this approach?
So that's a great question, and thank you. The answer is it doesn't work yet. We're about halfway through implementing this, though. The way that we intend to do it is essentially attaching a whole bunch of constraints. Is this one? Yeah, okay, sorry. So attaching a bunch of constraints is essentially the same as modifying the cost function. So since we're doing all of this symbolic generation, what we intend to do is take our symbolically defined constraints and use them to augment the constraint equations. What you can then do is you can essentially attach a weight to those constraints and first run the solver without any constraints and then iterate through in kind of a super loop around the solver that would dial that parameter, those parameters.
Like a bi-level optimization problem, where the inner loop would, where the outer loop would ensure that the constraints would be satisfied and the inner loop is just running your current problem.
It's more like you solve the problem assuming that you don't have the constraints, and then you slowly increase their relative weight in the cost function up from 0.
Okay.
And you use the result of the unconstrained the optimization problem solved without those constraints as the initial guess for resolving it with more weight on the constraints.
Makes sense. Thank you very much.
Thank you. I don't believe we have time for another question, unfortunately, unless someone will. Oh, wait, is this the last talk?
I think there may be time for one more question.
And there should be plenty of time for questions. All right, fire away. Do you want to go to the picture and then come back and I'll answer any of your questions?